We now understand that an atom will hybridize some of its atomic orbitals in order to make the hybrid orbitals necessary to form covalent bonds. The number of atomic orbitals that are hybridized will depend on the number of electron domains surrounding the central atom, and the resulting arrangements of the hybrid orbitals will match the geometries predicted by valence shell electron pair repulsion theory. To determine the hybridization of a central atom, we simply draw the Lewis structure of the molecule. Then we determine the number of electron domains around the central atom. This includes single bonds, double bonds, triple bonds, and lone pairs. From this number, we can know the number of atomic orbitals we have to combine to assign the specific hybridization and arrangement of the hybrid orbitals. Let's take one more look at this chart to see how all we need to know is the number of electron domains there are around an atom, and the rest takes care of itself. We should note that hybridization was developed in order to explain experimentally observed molecular geometries, and it holds true for molecules with small central atoms, like carbon, nitrogen, and oxygen. But as the central atom gets larger, the valence electrons get further away from the nucleus, and will thus exhibit less repulsion. Therefore, as the central atom gets larger, we begin to see bond angles that are less and less consistent with hybrid orbitals. For example, a water molecule has bond angles very close to the 109.5 predicted by VSEPR theory and hybrid orbitals. But if we go down the periodic table, changing the oxygen atom to a sulfur atom, we can see that the bond angles are actually closer to those that would result from unhybridized p orbitals, which are 90 degrees apart on the three axes. And if we go to a much larger atom of tellurium, the experimentally observed bond angle is now 90 degrees, which is achieved when the 1s orbitals in the hydrogen atoms overlap with the unhybridized p orbitals of tellurium. No hybridization whatsoever is necessary to explain the structure of this molecule. Therefore, we will use hybridization when we need to, especially for elements in the second period, but it is not a universal rule that applies to all possible molecules.